It's time for another amazing chemistry video with Mr. Stapleton. Grab this one, sit back, I'm doing a nice coffee.
Hi guys, this is the final video in the organic chemistry topic. I know there's quite a long topic, this one. There's been quite a few videos for it as well. But this one is finishing up with proteins, and this kind of draws together a whole bunch of stuff we've been looking at around amines, carboxylic acids, amides as well. And we kind of bring all those together as we start to get into a little bit of biology as well. So earlier this year, this is 2018, earlier this year Farmers Union brought out this drink, alright, so they brought out their Edge, which was sort of their breakfast, but they were talking about their breakfast cereal to come out, and it has a lot of protein in it, and we're going to be looking at what protein is, and I guess why it's important in terms of us for biology. So the first thing we want to have a look at is what we call amino acids. So amino acids are kind of like the building blocks of our bodies. We use them to make proteins, right? And they're really, really important. You can see we've got a general amino acid structure over here, and this is something that I guess you need to know for Year 12 chemistry. You're going to ask you about the general structure of amino acid. So I've actually got it in a three-dimensional form here, which hopefully you can see, and I've tried to match it up to what you've seen there on the screen. So what you've got down this end is an amine here. So we've got a nitrogen with two hydrogens on it, so it's a primary amine. Okay, you've got to remember that amines are bases. So this has a lone pair of electrons on it up the top here, which can accept a proton, which is important. Down the other end over here, we have a carboxylic acid group. So we've got the very polar carbon double bond oxygen here, the carbonyl group, and then we've got this oxygen to hydrogen here as well. So the amine here can hydrogen bond, alright, the carboxylic acid group here can hydrogen bond as well. We've only got a small non-polar organic sort of carbon in the middle here, okay, and so lots of hydrogen bonding here, so as you'd expect, these are quite high melting point solids at room temperature. Now, the central carbon here has one hydrogen on it, you can see, and then we've got this, what I've got just represented here by a yellow atom, which is what changes within our amino acids. Okay, we have 20 different variations on that yellow. Okay, so each of those 20 different variations are a little bit subtle, but they look a little bit like this. Okay, so what we've got is we've got 10 of the groups which are non-polar. So you can see we just start with hydrogen, which is glycine, then we go to one carbon and then 3 carbons on there. Alright, then we go to a carbon with a sulfur on it. Okay, we then go to proline, which actually has the carbons in a link back to the nitrogen. Okay, we have leucine, which has more carbons, but you can see that a common thing that all of these has is just a lot of carbons on the side chain. Alright, they're all non-polar. We've got 5 that are polar. Okay, and you can see what these have got in common is they've either got an alcohol group like serine and threonine here, or tyrosine, so that's got an alcohol on each of them here, or we've got a amide group, so asparagine and glutamine here. Both of these have amide groups on them, which makes them polar. We've got 3 of them that are charged, so you've got protonated amines on each of them here. Okay, and we've got 2 with a negative charge here, which are deprotonated carboxylic acids. Okay, so all of those still have this general amino acid structure, alright, but the R group changes between 20 different types. Now, you might notice here that these ones are a little bit different, and I'm going to explain what that means in a minute. But basically, inside your body, with the 20 different amino acids that we can have, there are 11 that your body can make, and they're what are called non-essential amino acids. So they're these ones here. Okay, your body can make these. However, these ones on the side, okay, these ones are called essential amino acids, because these can't be made by your body. You have to get them from foods and things that you ingest. Probably the main one through here that you might have heard the most of is phenylalanine. Alright, this is quite often used in caffeine drinks, okay, as a substitute for sugar, I think it is. And so if you look at like things like Pepsi Max or other things like that as well, or Coke, they'll quite often have phenylalanine on there, and there's been a lot of debate over the years around whether it's good for you to be having those from those drinks or not. Anyway, the main thing is that these 9 here, and you don't have to remember the names of them, okay, we'll leave that to biologists, but all you need to know is that there are some of them that aren't made in our bodies, and so these 9 here have to be made, we have to get them from foods. Now you remember I pointed out on that diagram around how some of them were drawn a little bit differently. That's because you have, if I bring my molecule back up, because you've got this carboxylic acid group down this end, okay, with a hydrogen on it, and you've got a nitrogen here which has a lone pair of electrons, what can happen is that this hydrogen can come off the carboxylic acid, okay, to form a deprotonated acid here. And what it does is this hydrogen actually bonds onto the nitrogen there to make a protonated amine. And what we call that is self-ionization. So we've gone from having a neutral molecule, alright, such as this one here, alright, and what we've done is we've taken that hydrogen off and we've bonded it onto the nitrogen to form a self-ionized molecule. Now what we call that is a zwitterion. Okay, so if you ever hear anyone talk about a self-ionized molecule, you can sound very smart and say, oh, you mean a zwitterion? And they'll just look at you a little bit strangely maybe and wonder how you got so smart. Make sure you point into my videos if you do that. So what they're going to do in Year 12 chemistry is they're going to ask you to draw amino acids at different pHs. Okay, so at a low pH, so we've got acidic conditions here, we're going to protonate our amine. Right, but we're going to leave our carboxylic acid alone. At a neutral solution, we're going to have our zwitterion formed, where we have both the deprotonated carboxylic acid and the protonated amine. And at a high pH, we're going to deprotonate the carboxylic acid but leave our base alone. Okay. Now that's nothing new, that chemistry, because we covered that in the amine and the carboxylic acid sections. We also looked at it when we hydrolyzed esters and amides as well. So hopefully it's really nothing new to you, but you really need to know this chemistry, okay, around what happens to an amine and a carboxylic acid at different changes in pH. So if you might want to pause this video here, make sure you look at the screen, make sure you can remember it. I'm not going to do it too much more depth, but hopefully it's pretty straightforward for you. Now, when we get amino acids together, because we have an amine on one end and a carboxylic acid on the other end, we can do a condensation reaction to form a amide. Okay? However, because we've got one on each end, we can keep going and form polyamides. Now, when we're talking about polyamides that are made from amino acids, we often call those polypeptides. And what we also sometimes call them is proteins. So a protein is a polypeptide, which is a polyamide. Okay, so not all polyamides are polypeptides, and not all polyamides are proteins, but all proteins are polyamides. Hopefully that's not too confusing for you. What that means is that every protein is made up of lots of amide groups joined by, which come from amino acids joined by condensation reactions. So this is the amide group here, or sometimes called the peptide group, and the peptide link they're talking about is this carbon-nitrogen bond between them, which is formed through the condensation reaction. Now that becomes important when we start going into proteins. So we're going to have a little bit of a look at some biology here as well. So when we're talking about the primary structure of proteins, we're talking about the way that the 20 different amino acids link up. And so what we've got here is a section of a protein here. Now proteins can have thousands and thousands of amino acids joined to each other. Okay, we've just got a section here. Alright, where it's going through, and you can see here we've just highlighted 4 of them: cysteine, leucine, I think phenylalanine. I don't know what this one is. As I said, we don't need to know the naming of them, but you can see we get a different structure as we go through here as they link up together. Now, as soon as you change, if you take out this leucine and if you put a glycine in there, it makes it a completely different protein. And that's really important because that basically is what gives us our coding and what makes us unique as individuals. You don't have to know all the process around like transcription and translation and codons and everything like that, which if you're doing Year 12 biology you might have covered. For the purpose of Year 12 chemistry, what we're looking at here is simply how they link up together via that condensation reaction is what makes what we call the primary structure. Now when you've got a long chain like this, you can imagine, you can see as the chain starts to fold on itself that you start to get interactions between the amino acids that have made up the polyamide. And so when you get the amides here that we've got interacting with other amides, you can get hydrogen bonding occurring, as you can see here. Now that hydrogen bonding is what determines what we call the secondary structure of the protein. And so there's two ways that these amides really link with each other and cause the protein to fold in on itself. And one way is you can get, if you get sort of this chain which folds just nice and flat, so I liken this to a, if you've ever had a flake chocolate bar, where you can see like sort of just those layers of chocolate on top of each other. My favourite is always if you've ever had a Viennetta ice cream, where you just got those folded layers. It's so good. Like that's basically what you got. That's called a beta pleated sheet here. The other thing you can have is sometimes you might get actually winding around itself. Okay, so that's what we call an alpha helix. And you've probably seen something similar like that if you've done anything to do with DNA. You know, the DNA is an alpha helix as it winds around itself, and that's due to hydrogen bonding between the bases that you've got on your DNA. When we're talking about a protein here, we get hydrogen bonding occurring between the amide groups, and that gives you your secondary structure. Okay, I do have a YouTube video on the secondary structure and looking at the impact that has and how you draw the hydrogen bonding. Alright, so I suggest you have a look at that. And then what you can also have is interactions between the side chains. Right? Now remember, there's 20 different side chains because there's 20 different amino acids. So and there was different categories. So 10 of them were non-polar, 5 of them were polar, 3 of them were positively charged, 2 of them were negatively charged. So it allows for a lot of opportunity of different interactions between those side chains. So the first one I'm going to have a look at is this one here, which is an ionic bond. So if you've got one of those positively charged side groups and you've got one of the negatively charged side groups here, you can get an actual ionic bond formed between them, which is very, very strong. Okay, if you have, I haven't shown here, but if you have a charged one here, so one of these positively charged ones, and then a polar group over here, like if this was one of the OHs on those 5 polar side chains you could actually have ion dipole interactions as well. Over here, if you just got 2 polar ones next to each other, you can get hydrogen bonding occurring, which is quite strong. Right here, if you just got 2 non-polar side chains next to each other, you can get dipole-dipole interactions. And over here, if you get 2 cysteines next to each other, you can actually get a sulfur-sulfur cross-link between them, which is a primary bond, but it's a covalent bond, so it's the weakest of the primary bonds, but it's still quite a strong bond. You get this quite often when you're doing your hair. If you style your hair after getting out of the shower, when you wet your hair, you form sort of these sulfur-sulfur cross-links between your cysteine side chains. Alright, so these 3 interactions are really the ones that we're going to focus on here. The hydrogen bonding over here, some ion dipole interaction and disulfide links, because they're the ones that can be influenced by temperature and pH, which is what we're going to be looking at. Again, there's a video here which I've done on the tertiary structure of proteins, so if you want to have a look at that, I suggest you do it, and it just talks again through the different interactions you can have. But what you need to understand is that enzymes in our body are actually proteins. So an enzyme is a biological catalyst, and I think we looked at this right back in like the very first topic when we were looking at rates of reactions, and we introduced this whole lock and key mechanism for an enzyme. So what you have is an enzyme over here, which is a protein, and you can see it's got a specific shape in here, specifically designed to have these substrates come in and react. So these 2 substrates come into the enzyme, alright? Because they line up really nicely together, this increases the rate of a reaction quite significantly, and we get our reaction occurring much faster at the active site. We then get our products coming out, and then you can see that the enzyme is still available again to do another catalyzation inside our body. So this is our body's way of speeding up organic reactions which are really, really slow. You can see here, and this is a really good example, how this protein here, this enzyme, has a very unique shape in the middle, and that's specifically designed to only allow these substrates to come in. Okay, so this is the lock in here, and only allows these keys to come in and fit it. If you have something else, it doesn't work. All right, so that's why it's really important that we get the folding and the structure of the enzyme, which is a protein, correct to allow for this lock and key mechanism. Now what happens is that if the shape of the enzyme changes, you can no longer get these substrates coming in, all right, and bonding to it. So now that the shape is different, okay, we can no longer get the substrate coming in, and so we can't catalyze the reaction. And this is called denaturing of an enzyme. So denaturing of an enzyme isn't killing it, it's simply changing its shape. Once you change its shape, it can no longer perform its biological function, and that's really key. Alright, and those the way it changes its shape is if we change the pH or the temperature. Okay, now the pH and the temperature have an impact upon those three types of bonds: the hydrogen bonds, the ion dipole, and the third one was the hydrogen bonding. So ion dipole, hydrogen bonding, and let me go back to it. Sorry, and the disulfide links as well, because we're putting energy in. So let me show you what we're looking at here. When we change the pH, this comes back to the ability to protonate an amine or deprotonate a carboxylic acid. So when you have a low pH here, you've got protonated amines, but you don't have a deprotonated carboxylic acid. When we go too high in pH, we have deprotonated carboxylic acids, but we don't have a protonated amine. You can see we also have an impact upon the sulfurs as well. Alright, where we deprotonate the sulfurs on the cysteines that we've got here, and so that impacts the sulfur-sulfur cross-links we get as well. So when you change the pH, you're going to really impact those ion-dipole interactions, because if you have a or even an ionic bond in there, alright, if you protonate the carboxylic acid in an ion-dipole bond, you're going to break that bond, which is going to change the shape of the molecule, because it's no longer going to hold those two sections of the protein together. As soon as you change the shape of it, what happens is that the whole molecule changes shape and it can no longer perform its biological function, so you've denatured it. If we're talking about temperature, we know that if you supply energy in the form of temperature, alright, you are increasing the speed of the molecules, or how fast they move. And what happens is that as you start to increase the speed or increase the temperature inside your enzyme, what happens is you can break those hydrogen bonds, or you can break the ion dipole interactions. It's normally the hydrogen bonds or the secondary dispersion bonds in there that are affected most by the temperature. As soon as you break those bonds, your protein unravels, okay, and it becomes denatured and can no longer perform its biological function. Now, every protein or enzyme has its optimum operating temperature. So you can see for this protein here, it's around about 40, probably 1 degrees, something like that, just here. Okay. Lower than that, and what happens is that the protein, because it's colder, the protein sort of condenses in on itself, so the structure isn't necessarily exactly what it should be, and so what happens is that the reaction isn't catalyzed as fast as it could be. What happens as you increase the temperature, so as we're going down this graph here, is that you start to get the bonds to come further and further apart, and you get to a point where they break. Okay, and that breaking of the bonds is this point here at 60 degrees. That's where the enzyme is denatured. Okay, and so the rate of reaction significantly decreases. All right. For this topic on proteins, they're really going to ask you around the structure of amino acids. Right? They're going to ask you to draw the zwitterions, and both at low and high pH. So I suggest you can do that. And then they're going to ask you around the secondary and tertiary structure of a protein, and talk about the type of bonding that's present there. And in particular, they're going to look at the effects of pH and temperature upon that bonding, and how that denatures enzymes and stops them from performing their biological function. So I know that this one has been a slightly longer video to end off, and I've needed to go through it, but I'm just going to end you with some very wise words from Captain Jean-Luc Picard, which says that if organic chemistry was easy, it would be called biology. For my students, this is the end of the Year 12 chemistry course. Hopefully it's all sort of come together, but always go back, have a look at the videos, and if you've got any questions, just ask. Thanks, guys.